Welcome to our exploration of force by massless particles and its conversion into energy. In classical physics, Newton's second law is a cornerstone for understanding force, but it mainly applies to particles with mass. Today we dive into the limitations of this law and discover how force can be defined for massless particles like photons. We'll also see how force and energy are interconnected, revealing new perspectives in modern physics. Let's begin by setting the stage for why this topic matters in both theoretical and technological contexts. Newton's second law states that force equals mass times acceleration. This linear relationship has been invaluable in engineering and technology. However, it assumes the presence of mass, which becomes problematic when we consider particles like photons that have no mass. Despite its widespread application, Newton's law cannot fully describe the behavior of massless particles. This limitation prompts us to seek new mathematical frameworks that can handle quantum phenomena and the atomic scale. Classically, force is defined as a push or pull. While this definition works for everyday objects, it falls short at the quantum level. Quantum mechanics offers a more nuanced view, especially for particles without mass. By redefining force mathematically, we can better describe the behavior of massless particles. This shift from classical to quantum thinking is essential for understanding the universe at its smallest scale. 2022, a groundbreaking paper introduced the concept of rest wavelength for particles with rest charge. The formula for rest wavelength incorporates fundamental constants like Coulomb's constant and the speed of light. This equation bridges the gap between mass and wavelength, providing a new way to understand how massless particles behave. The rest wavelength is crucial for deriving the force formula for massless particles. Speed of light, denoted as c, is a fundamental constant in physics. It can be expressed in terms of the permeability and permittivity of free space. This relationship is essential for understanding how massless particles, which always move at light speed, interact with their environment. By connecting these constants, we lay the groundwork for a new force formula that applies to both massive and massless particles. By manipulating the rest wavelength equation, we can express mass in terms of fundamental constants and the rest wavelength. This mathematical transformation is key to extending Newton's second law to massless particles. It allows us to substitute mass with quantities that are meaningful for particles like photons, paving the way for a universal force formula. Newton's second law relates force, mass, and acceleration. For massless particles moving at the speed of light, we substitute mass with our new expression. This leads to a force formula that depends on constants, rest wavelength, and time. By further substituting Coulomb's constant, we refine the formula, making it applicable to massless particles like photons. For particles moving at light speed, the period t is the inverse of frequency f. This connection is vital because massless particles, such as photons, are characterized by their frequency. By substituting frequency into the force formula, we obtain a relationship that ties force directly to the oscillatory nature of these particles. Refined force formula now includes permeability, charge, and frequency. This general formula works for both massless and massive particles. Unlike classical mechanics, where force is simply a push or pull, this formula reveals that force involves oscillation. It captures the dynamic behavior of particles at both quantum and classical scales. The charge of a particle in motion can be calculated using the reduced Planck constant and Coulomb's constant. This calculation is essential for applying the force formula to real-world particles. By understanding how charge varies with motion, we gain deeper insight into the forces acting on massless particles. Oscillation is a key feature in the new force formula. Instead of viewing force as a simple push or pull, we now see it as an oscillatory phenomenon. This perspective aligns with quantum mechanics, where particles exhibit wave-like behavior. Oscillation connects force to energy, setting the stage for force-energy equivalence. Special relativity teaches us that mass and energy are convertible. Similarly, force and energy can be interchanged. The force formula, when combined with charge and frequency, leads to a new equation that expresses energy in terms of force and frequency. This equivalence opens up possibilities for extracting large amounts of energy from small forces. By substituting charge and frequency into the force formula, we derive an expression for energy. The equation shows that energy can be obtained by multiplying force by the speed of light and dividing by frequency. This mathematical relationship mirrors the mass-energy equivalence in relativity, but now applies to force. Imagine oscillating a bottle of soda. The oscillation creates force, which can lead to an explosion if the energy is high enough. This everyday example illustrates how oscillated energy can be converted into force, as described by the force-energy equivalence equation. The mystery behind such phenomena is now mathematically explained. Force-energy equivalence has profound implications for technology. Understanding how energy can be extracted from small forces could lead to new innovations in energy generation and storage. This principle may also impact fields like quantum computing and advanced materials, where massless particles play a crucial role. Quantum mechanics provides the framework for understanding massless particles. The new force formula aligns with quantum principles, emphasizing oscillation and frequency. This perspective helps us describe phenomena that classical physics cannot, such as photon interactions and atomic scale behaviors. The general force formula derived here is universal. It applies to both massless and massive particles, bridging classical and quantum physics. This universality is a major step forward, offering a single mathematical expression for force across different scales and types of particles. Energy conversion is a central theme in physics. The force-energy equivalence equation shows that oscillated energy can be transformed into force, and vice versa. This principle is not only theoretical but also practical, influencing how we design systems and understand natural phenomena. Let's recap the key equations: Newton's second law for massive particles, the rest wavelength formula, and the universal force formula for massless particles. The force-energy equivalence equation ties everything together, showing how force and energy are fundamentally linked. These equations provide a comprehensive toolkit for modern physics. For those interested in deeper exploration, the references cited include works by Wilczek, Grainer, French, and others. These sources provide foundational knowledge in classical mechanics, relativity, and quantum physics. Studying these materials will enhance your understanding of force, energy, and massless particles. Conclusion: redefining force for massless particles and establishing force-energy equivalence opens new horizons in physics. This approach not only addresses the limitations of classical laws but also integrates quantum principles. As research continues, these concepts may lead to breakthroughs in technology and our understanding of the universe. Stay curious and keep exploring the mysteries of physics.